to start the discussion, we need to go back to the series solution. So for the solution for the Bessel function, for Bessel equation, we discuss how you get the series solution. The series solution, we got it from either the ODE chapter or in section 1, we used the generating function for integer and integer order, and then argue that for arbitrary real order, you can also use the same series solution, except you change one of the factorial to the gamma function. But the same formula actually show that using just plug in the series to the Bessel equation, you show that this is the solution. This is textbook using S in the summation in variable -1 to the S factorial nu plus S plus 1 x over 2 nu plus 2S. Okay, and then we this is for nu, and then you can use nu or minus nu or minus nu. If you change minus nu, you just substitute minus nu in here, minus nu in here, and it's still the same solution. So for the Bessel equation, you have for general nu that is non-integer, we have supposedly two solutions, two linearly independent solutions. The gamma, that's j sub nu or j sub minus nu. And we'll make it explicit y to show that it's linearly independent right away. But we also pointed out that if you let nu go to n, so you have two solutions, n and minus n. We are also showing that we show that this when the nu equals to minus n, actually proportional to nu n. So j, show that j minus n is equals to -1 to the n factor, n power j sub n. So they are linearly dependent. So they are not. We only have one solution for integer. Nu is integer. Okay, and one difference between integer and non-integer orders is the property near x equals 0, right? Near x equals 0, so obviously you keep just the first term s equals 0, right? So the two terms for nu and minus nu, one is x to the nu, and assuming nu is positive, this is n is positive, so for positive nu, the j nu is regular because it's x to the power nu, so it's non-singular. But the other solution, j sub minus nu, you have x to the minus nu power near x equals 0. So that's a singular solution at near x equals 0. So that's different. But for integer order, then that is not so because of this relation. Obviously, if j sub n is regular near x equals 0, j sub minus n is also regular. So different from the seemingly you have this dependency. So if you substitute nu equal minus n, supposedly you have x to minus n. That looks singular, but that is not so. So you can look at it two ways. So the first way is using the generating function. We show that actually the summation is for this case minus n is not starting from 0. So we did that. But another way to do that, you actually use the same formula and take the limit nu equals to minus n. And you see that when you sum over s from 0 to infinity, that you go through some of these argument of the gamma function as negative integer. And you remember that the gamma function at the negative integer, including 0 and negative integer, they are all singular. So they're all infinity. So the coefficient of this power series for negative integer argument in the gamma function will give you 0 until you get to the argument equals to should be to 1, because 0 is also 0 is still singular. So the s, all this s up to, so if it is 0, then s equals to minus nu minus 1. So up to s equals minus nu minus 1, right? Start from 0. And remember that we're using nu equals minus n in this case, in this discussion. So this is like this is n minus 1. So summing s from 0 to n minus 1 with positive n. All the coefficient of this power series are 0 because of the singularity of gamma function. So you actually start with s equals to n, right? All these this is n minus 1, right? Start with s equals to n, right? And then so there's 2s becomes a 2n. Nu is minus n, so 2n minus n is n. So you actually get to x to the n power, just like the property of the j sub n, which is required because of this proportionality. So the difference between integer order and non-integer order is significant. And now, but we still have to choose another solution for integer order, because these two solutions, nu and minus nu, becomes a linearly dependent. So we need to define another solution for the second solution, because the Bessel function, the Bessel equation is second order. It has two linearly independent solutions, right? And to do that, we discuss it slightly different from the textbook. We are rearranging the order a little bit. We talk about how you consider whether they are linearly dependent or non-independent first, and then suggest the form of the definition of the second linearly independent solution for integer order. Okay, and to do that, we need to look at the Wronskian. The Wronskian depends on the form of the differential equation, obviously. So you can write down the solution. This J nu is the solution of this Bessel equation. This is equation 14.1 plus x squared minus nu squared J nu 0. So for j sub nu and j sub minus nu satisfy the same equation, because the coefficient depends on nu squared. So whether it's nu squared or minus nu squared doesn't matter. Well, now we look at the Wronskian. Remember the Wronskian is if then consider too the general solution doesn't necessarily have to be J or what. So you have to say like two solutions, C sub 1 and C sub 2, right? Both satisfy the same Bessel differential equation. Now we consider the Wronskian of C sub 1, C sub 2 is defined as, well, you can write down it's easier to remember the matrix form, but you can write that because this is just two functions that you can write like write out explicitly. doesn't matter. This C sub 1, C sub 2 pi, minus C sub 2, C sub 1 pi, right? So we had the discussion in the ODE chapter that when the Wronskian is 0, then they are linearly dependent. When they're non-zero, they are linearly independent. We need to look at the Wronskian for different combination of the C sub 1, C sub 2, right? And now we can just actually plug in what we had in the ODE chapter for whatever this the form of the ODE. We put it in the standard form like whatever P and Q in the coefficient, and then plug in the formula. And if you still remember the formula, you can use that. But for this equation, because it's a second order, it's so easy to rederive that. So even if you forget about all this, the formula, you can just consider like a dw dx or w pi. So let's just skip the same notation. The w pi, the derivative of w. Now, just plug in this form, and you can use the derivative of the determinant just we talked about before. But for this simple case, you can just take the derivative of that. So you have two terms. One is C1 pi, C2 pi. The other is C1, C2 double pi minus C2 pi, C1 pi minus C2, C1 double pi, right? Just straightforward derivative, and then you see that this cancel. And now you have C1 double pi and C2 double pi, and you can now use the Bessel equation. C1 and C2 double pi is just moving everything to the left hand, to the right hand side divided by x squared. You get minus C2 pi over x minus the other side divided by x squared, 1 minus mu squared over x squared, C2. And do the same thing for C1 double pi here. C1 double pi is minus C1 pi over x minus 1 minus mu squared over x squared, C1. Right. Now you see that this multiplied by that is the same as this multiplied by that, and this is negative sign. This is make a negative positive sign. Okay. You see that this cancel. This one cancel with this one. Right. And then this two, C1, C2 pi, there's a negative sign, and C2, C1 pi, and positive sign, and combine to be exactly this one with the negative sign, and then divided by x. That actually is minus w over x. Okay, you see that? So finally, we talked about this before, so this is just a kind of reminder. The w pi is that, and you know how to solve this differential equation, right? W pi equal w. It's just a simple integration. This is first order, so w will be equals to some constant exponential function, because the solution is an exponential function, right? So it's this w pi divided w integrated log w, right? And then the log w becomes an exponential function of the integration of this coefficient dx over x, and that integrate to log x, right? It's w0 exponential minus log x, right? So that equals to w0 over. Okay, so they proportional to 1 over x here for the Bessel equation. So all the whatever the solution of the Bessel equation, so any two of them, the Wronskian must proportional to 1 over x. Okay, so that is the property. And now that that allow us to evaluate the Wronskian for this solution like j sub mu and j sub minus mu, because all we need is this, because we have a power series, supposedly many order, but then we only need to look for the term that gives us the 1 over x. Right? Okay, and that would be enough, because that's the exact form. The whole thing is exact. So wherever we get the 1 over x dependency out of the whatever expression, like the power series, and a slightly easier way to do it is using the asymptotic series, asymptotic solution. That would give you an easier way to get the coefficient. Just fix that coefficient. But using a power series is also okay. So it's okay. So that is our goal is to find use the power series solution and to fix the coefficient in the Wronskian. Right? And that's what we do. And so this is just the derivation. Now we go back to the series solution and to get the form of the Wronskian, right? And now the series solution, if we take the limit of x goes to 0, then we get all the other high order term in S will goes to 0 faster than S equals 0 term. You only need to keep S equals 0, right? And so that is one way to do it, because we only need the form that gives us 1 over x, and whatever limit of the solution is fine. So we take the limit of x goes to 0. Because of course we are looking at the positive x anyway. So you can see that J nu is what tends to just keeping an S equals 0 term. So that is 1. This is 1, and this is gamma nu argument nu plus 1, right? And then you just keep S equals 0, so x nu. Okay, so that's J nu. And now J minus nu is still we're keeping the minus nu, just S equals 0, that will give you minus nu, right? We already discussed that. And which is for a positive nu, that is singular. Although it's singular, the leading order of the singularity, the largest term, is still given by S equals 0. So we only keep that term. So that one goes to now S is 0 again. And now you change nu equal minus nu, because we are explicitly using minus nu here. Gamma minus nu, or you can write 1 minus nu, right? And then x over 2 minus nu. Okay, is that okay? So that is the limit of this of the J nu and J minus nu. Now we need the derivative also in the Wronskian. So J nu pi, we just goes to, so you have a nu and x to the nu minus 1, and then take the derivative of the argument, which is 1/2. Plus 1 x over 2 nu minus 1, right? And J minus nu goes to, will give you minus nu, and then factor of 2, gamma 1 minus nu, 2 minus nu minus 1, right? So now we have everything. So the Wronskian is, say, define a J nu, J minus nu pi minus J nu pi J minus nu. Now that one is using this limit of x going to 0. Just plug in everything. you have this times that. So you have the denominator is gamma 1 plus nu times 1 minus nu. You have a factor of 1/2. And you have a minus nu in the denominator. So that is this one. And this term is this one. It's this one. Did I write? No, this term is this one times this one. So, no, this one times j, this times this one, right? Yeah, and this term is this times that one. But this times that one, you still have a nu here. The denominator is still gamma 1 plus nu times gamma 1 minus nu and factor of 1/2, right? And then the x to the power is x over 2, nu. But this times that is, you cancel the nu term, right? Nu factor, so nu minus nu. So you only have minus 1 factor. This times that, you have nu, you have minus nu. Still, you only have x over 2 with the minus 1 factor. Okay, and so combine everything. So you have two terms, so both have this. The sign is important. The first one is minus sign. The other is positive sign, but you have minus sign here. So altogether you have minus. And you have a denominator as gamma 1 plus nu, gamma 1 minus nu. And you have a factor of 2 in the denominator, but you have two of them both are the same, right? And so you cancel the factor of 1/2 here. So you only have that one. And then only have x over 2 to the minus 1 power. Is that okay? Can you see that? Yeah, and the nu, yeah. Yes. Yeah. Yeah. Right. You can see that, right? So now we are fortunate that we get the 1 over x power here. So we know that this now is, instead of a limit, it actually is exact form because we know that the Wronskian must be proportional to 1 over x. But we got the 1 over x term right here. Okay, so that is we can say that is your answer, but we wanted to get more insight. So we need the property of this gamma function, and that is actually exactly the refraction formula. And let me look that up. It should be the first section in chapter 13. That is yeah. This is 13.23. You can use 13.23 or equivalent to the next equation. That will give you the 13.13. This is gamma. Using the notation in the 13.1 is z gamma 1 minus z equals to pi over 9 pi z. Right, and then yeah, this equals to gamma 1 plus z divided by z 1 minus z. Right, this is just the property of the gamma function. And so gamma 1 by z times gamma 1 minus z is pi times z divided by sine pi times z, right? That will give you, now our z becomes nu, right? Z becomes nu. So minus nu and pi nu, right? And then sine pi nu. And then 2 over x. Right, and that should be the correct answer, hopefully. Look at your textbook. That is supposedly 14.67. So you cancel the nu. The 2 sine pi nu divided by pi times x. So that is 14.67. Okay. So that's the Wronskian of the between j sub nu and j sub minus nu. Both are the solution for the same Bessel equation. Okay, and now we see that this is non-zero when if all the nu is not integer, because sine pi nu is not zero for non-integer. It's only zero for nu equals to integer. So if nu equals to n, sine pi n pi is zero. So we can immediately see our conclusion. So for non-integer nu, then these two solutions are linearly independent. But for nu equals to n, the j sub n and j sub minus n are not linearly independent. They actually is zero for integer n. For integer order, nu equal to integer, so sine n pi is zero. So that is confirming our conclusion that Jn in proportional to j sub minus n. Okay, and that is the explicit look at why they are linearly independent or not independent. Now the Wronskian after this, after deriving this, you can use the recurrence formula to derive the next two equations, 14.68, 69. You can do that right away. I think some of these are exercise. And then the other two, the next two are based on the definition of this y function, what we call the Neumann function. Once we define the Neumann function, you can derive the next two quite easily. And so we'll just skip those discussion. You work on the exercise. Okay, but we'll go back to this this Wronskian to give us a suggestion how to define a second solution for integer order, because we know that the Wronskian has this sine pi nu in the numerator, so to make it zero. So one suggestion is divided this factor in your solution, and that will be the starting point. Okay, and now let's see what else we need. We probably need all of them. Let's just try to define this y sub nu, and we are suggesting that you have a sine nu pi or pi nu, doesn't matter, in the denominator, and because we wanted this to be a solution also for the same Bessel equation for the same nu. It must be a combination of j nu and j minus nu, and we also wanted it to be regular, even in the limit of nu goes to integer. When nu go to integer, the denominator is zero, right? And so we wanted in this limit, the whole ratio is finite. So we need to define the numerator so that it actually also goes to zero at nu goes to an integer. So you have a combination of j sub nu x, and j sub minus nu x, right? And then when nu goes to integer, we remember that j n is minus 1 n, j sub minus n. So we need this we need to use that, because when nu goes to n integer, you have this relationship. We are making use of that. So we define that with this minus 1 to the nu power But this minus 1 to the nu power, we can use that as using the cosine function, because the cosine pi nu. And the second term, we just subtract this too, right? Because cosine pi times n, if nu goes to n, cosine pi n is cosine pi n is minus 1 to the n, right? If n is 0, it's just 1, n is 1, is cosine pi is minus 1, right? So this one will goes to this minus 1 to the n power. And multiplied by this j sub n is the same as j sub minus n. So that one will go make it goes to 0. So both numerator and denominator will goes to 0 at the limit of nu goes to n integer. And then for non-integer, this is just a linear combination. That doesn't matter. So everything is regular. Cosine pi nu, sine pi nu, both are regular value. It's non-zero and non-singular. And just a linear combination of j nu and j minus nu, both are solution of the Bessel equation. So that makes it also a solution of Bessel equation, just a different linear combination of the two solutions. So that's fine. Now it's when nu is, when j is, when nu goes to n, right? Then these two are linearly dependent, but then the numerator goes to 0, the denominator also goes to 0. Hopefully that after we take the limit, we get the finite result, right? And that is the suggestion. But once we define that, we can just use the Wronskian of this one to see the Wronskian of j nu and j y nu. What is that? And see if we get a finite result instead of a j sine pi nu. So we want to do now w of j nu and y nu. Right. And now we just need to plug in this expression into here, right? So Wronskian of j nu, and you have this cosine pi nu, j sub nu minus j sub minus nu, and sine pi nu, right? And the Wronskian for the first term in the second slot, that will give you 0, because we know that the Wronskian of j nu and j nu, so it's 0, because by the definition of Wronskian, you know that if you both are changed, then it's j nu pi minus j nu pi j nu, that is totally 0. So, and then these are just coefficients that by this definition just coming out. This coefficient is coming out, so that doesn't matter. But the first term will give you 0, and the second term will give you, just get the coefficient out, so you have minus 1 over sine pi nu, and then the Wronskian of j nu, j minus nu, right? And this one we already did that, right? We just got it here, so you just plug in everything, so 1 over sine pi nu, and just substitute this 2 sine pi nu divided by pi x, right? Now, there's a negative sign also, but with this negative sign, you cancel both the negative sign, cancel sine pi nu, so it's 2 over pi x. Okay, so that should be the other. This is 14.70. We already did that one. All right, so once we have the definition, we get this easily. And now you see that this is regular, right? This is always regular because 2 over pi over x, it must proportional 1 over x, we discussed that. But the coefficient will not go to 0, so j nu and y nu's are linearly independent. We define it this way. Is that okay? And that is for all nu, right? It's because the nu actually cancel. We define this with the nu actually cancel, so we can take the limit of nu goes to n, nu goes to integer, and still get the the Wronskian like that, and so it's still linearly independent. It's okay. So that's give you the suggestion why we could do that.